תוך כדי, it's an open discussion. זה המומנט שלך.
לראות את הים,
רואים בסדר? כן, יופי.
אמא שלי הייתה לקחת אותי 3 פעמים בשבוע עם אוטובוס לים, זה לא שקט. גרתי באזור חליסה.
אבל...
בסדר,
אבל אוטובוס יש פה אפילו שבת לים אפשר לנסוע.
בדיוק, זה מה שאין אצלנו.
יותר טוב? Okay, I'm very excited. I used to give this lecture in English for Josue or in conference in English, so we can do both if you want to ask in Hebrew and English, whatever you like. Maybe we're going to change in the middle. So I'm going to present to you the electrostatic effect on inhaled aerosol deposition in the deep airway of the lungs. And before that, let's start with basic, with some, צריך ללחוץ פה. זה עובר? הנה. Okay, with some basic motivation and background. So when somebody considers drug delivery, there's many methods to do it. So why to go with inhalation versus the other methods? So first of all, if you're thinking about topical treatment, localized treatment, the airway is an open door. You directly go to the location where you want to treat. And also this is very rapid. Inhalation sequence is only 4 seconds approximately. And also interesting thing, if you want to treat in a systemic perspective, this is maybe more relevant to Nati, you can go through the blood system that connect to the lungs. And you can think, for example, Afresa is a company that give inhaled insulin already in the market. And the advantage is that less degraded and highly dispersed after the lungs to the heart and to all the body. And it sounds perfect, it sounds good, but what are the limitations? Where's the problem? The problem actually can be found in this graph, and we're going to come back to this graph in the end of the presentation. So I'm going to show different particle size that somebody inhale and the deposition fraction, how much stay in the lungs, how much exhale. So if you want to target the alveoli, so the distribution goes something like this. You need to be really small to get to the alveoli. And if you want to treat the bronchioles, the distribution look like this, but most of the medicine actually deposit in the upper airway, in the head and the throat. And that's how it looks. And somebody would think, no problem, we can target the alveoli or the bronchioles where the disease are by producing this small size of particle, but unfortunately this is unreachable in off-the-shelf inhalers. So we live in this kind of window, and actually the effectiveness of drug delivery is something like this, which is really, really low, and most of the drug, as you can see, go to the upper airway. So we're looking for a solution for that, especially for kids. In kids, the situation is even harsher. The velocity is faster, the size of the throat of the kid is smaller, so stock number is big. So what we're going to do, what I'm going to talk today is about electrostatics effect. You see this kid slide down the slider, doesn't feel any electrostatics, but his hair tips are very thin. And for that reason, the ratio area per volume is huge. And for that reason, hair tips very sensitive to electrostatic. And something similar happened in the aerosol world. So when somebody see an aerosol get outside of inhaler, so because of triboelectricity, the aerosols is very, very small and also very sensitive to electrostatic effect, where the charge of the electrostatic is coming from. So if this an inhaler, neutralized inhalers, when an aerosol comes, it accumulates some excess charge from the inhaler and only then deposit within the human body. We can go over off-the-shelf inhalers, and we know from the literature they can accumulate some charge. Nebulizer, 1 electron, dry powder can reach to 200 electron per aerosol, and MDI 500, and in academic device we can do a very, very charged aerosols. So by triboelectricity, mostly this is the reason the aerosol getting charged, just the friction.
What is the minimal size you can still charge, because it's a problem of surface. You need some minimal surface.
It's a fight between the surface tension and the electrostatic. So if either you have too much charge that's going to wrap up the droplet, that is kind of the limitation for how much you can charge.
Solid particle.
Solid particle. So what's the question about solid particle?
What's the minimal size you can still charge?
The minimal size of an aerosol that can be charged?
Yes, because the charge, the charging,
The charging mechanism.
of the surface area.
Definitely.
If you have very little surface area, you actually have problem to charge the particle.
You don't have space to distribute the charge. You're gonna have a repulsion. I don't know the theory behind what is the limitation on small dry particle that's gonna be charged. I'm not sure about that, but I can think it's related to the Fermi level and stuff like that, and the electrostatic repulsion, and also the two type of materials that you have. What is the dry aerosol? What is the surface that being? Because it's depend on the connection, the potential between them, probably. But I'm not that familiar with that.
Look at the electrostatic precipitator, which is in the commercial places like a power plant. Then you charge the particles when they go through an electrostatic precipitator, and the charging goes up dramatically with the size of the particle.
So what's the bottom size limitation? Do you know order of magnitude?
I don't really know, but you can see that they have like charts that they go up exponentially from.
I know.
Order of magnitude, but what?
To charge a particle is a function of its size.
Definitely. But what is the limitation for a small particle approximately?
Would you know off the top?
Yeah, of the like.
I think it will go to some tens of nanos.
Okay. It's very, very small. Tens of nanos. It's very, very small.
Wow.
Yeah.
You can have down to single charges on the outlet. Yeah, exactly. One sitting on that. Yeah.
Okay, so my question was, how does the electrostatic charge affect the deposition in the lungs? So in order to see it, you can think about the lungs to all its scales. And if you're going to zoom into the connection between the aerosols and the tissue, we're going to see that the interaction of the charged aerosol, it polarizes the tissue, and for that we have electricity force, the Coulomb force. And a key factor I want you to see in this presentation is that the force is inversely proportional to the distance. And for that reason, I expect this force to be very strong in the small region of the lungs, for example the alveoli, versus the upper airway, which are very, very big. So let's see what we have in the literature about electrostatic. So this group did a very interesting simulation. They expose small particles to the throat, head and throat, and so that when they increase the charge, they have more and more deposition in the upper airway. And also Muhammad Ali, I know the name is funny, but maybe he had a crisis at age 60, but he also built an in vitro model of the upper airway exposed to distribution of particle, and see that the amount of a particle deposit within multiplied by 3 times because the aerosol were charged. And also in our lab, if you know Rami Fischler, he designed an interesting model. I want you to see Donald Duck, how he's being kidnapped to outside the stage, because this is very similar to the electrostatic effect. So he did this cavity, and if you're going to zoom in, you're going to see that suddenly the aerosol being kidnapped into the wall. This is related to the 1 over the distance square. This force is very, very strong as you get close to the wall, so you have suddenly a very big acceleration. So we already knew that something is going on with the electrostatic and somebody needs to address it. So let's go and revisit the particle dynamics. So we have drag force, Brownian motion, gravity, and of course electrostatic. And the problem with this equation is that the electrostatic makes this equation non-linear. So the method to go over it is to use non-dimensional numbers. For example, the Stokes number, how much impaction versus convection we have, the Paclet number, how much diffusion play a role against convection, the gravity number, and also, not but not least, the electrostatic effect, the induced charge mechanism. And I want you to see that all of these sizes, all of these non-dimensional numbers, highly dependent on the characteristic length of the problem and the velocity. And what's really special about the lung is that the lung is a multi-scale problem. The generation change always in size and also in the velocity that we have depending on the flow that the person is breathing and where we are inside the lungs. Yes?
Where is the Reynolds number?
I'm going to get into the Reynolds number, but it's true. Reynolds number is more about the flow, the Reynolds of the particle, and it's determined which drag force we actually have on the aerosol itself. This is correct. So we're dealing...
It would be fair to say that if you're talking about the particle Reynolds number,
Exactly.
the minute you're under 10 micron, no matter what, you're probably just in air at, no matter how fast you would breathe, 10 to the -2 at very best, just because you're a micron, right? Like it's completely-
Yeah, Reynolds of the particle is very...
You will get to single one or two.
Because the Reynolds number doesn't exist per se
In the Newton second equation, that's true.
In the Navier-Stokes of the particle.
It actually do exist in the equation because in order to determine the drag, so the flow pattern determines the drag that we have. So we assume a linear Stokes drag on the particle for all the models that I'm going to show you.
You took the Cunningham factor
Yes, definitely.
on the Stokes, on the arrangement.
Yeah, of course. And also on the electrostatic, and it's appear everywhere because you have this tau, the relaxation time. So it's inside H, inside the diffusion, and also here you have the mechanical mobility, you also have the Cunningham.
So you took into account that the particle is following exactly the stream line?
It depends, it really depends, but it depends on the situation. So I'm going to show you the model when we go discuss it, but yeah, it depends. Okay, so there's some literature about the upper airway, but as I told you, in this region I don't expect the electrostatic to be the strongest, actually in the deep region of the lungs. So I decided to do the non-dimensional analysis between the forces and look who is dominant inside the acinar region. So I put a log scale of different kind of inhalers and charge versus the different size distribution. And as you can see, for the big particle, no surprise, H is dominant. For the small particles, no surprise, Paclet is dominant, the inverse Paclet, I mean. And for merely 20 electrons in the alveoli cavity, that's it. Electrostatic govern the equation, and for that I expect electrostatic to be very strong in the acinar region. And we decided to put that into a test and provoke the question, does electrostatic affect the position in the deep lungs? So let's go into the acinar, and I'm going to present you my model. So you can see here in the video my model, but I also brought it here today, so you can look at him if you want. But I'm going to right now explain the model. So the challenges in designing this microchannel model were that we want anatomical scales, the real scales, because the distance plays a significant role on the electrostatic charge. We want to have the same respiratory flow inside the model. And we wanted to have electrical conductivity similar to that one of the lungs. And we want the model to be transparent so we can see what's going on inside. And something very important that we can use is that the fact that our problem, like we day to day feel like the world is too deep. So similar thing happened in the acinar. When you consider an aerosol, his size is very small compared to the diameter of the alveoli. So for that reason, I can approximate that the aerosol don't know that he's actually facing a cavity. It just see a drop, it just see a hole, it just see an edge. So we're going to use this idea. We're going to use this idea that we have a septa and we have a cavity. So we don't need to design a 3D cavity, but 2D would work. And I'm not the first one to come with this idea. For example, this group did a cylinder with many grooves that resemble like a cavity-like feature. So how we did that? So in the clean room, I used dicer machine and curve into the glass 6 trenches that gonna present the alveoli. So if you're gonna zoom in into the bright field of the microscope, it's look like this. So we got the real geometry of the acinar and the septa in between them. And in order to have a conductivity, I use atomic layer deposition to cover my model with ITO. So 30 nanometer of ITO.
Just say what ITO means.
ITO, indium titanium oxide, it's a material that the most important properties for us were that he is conductive and both transparent. So we can still observe in the microscope what's going to happen inside the model. So this is the microchannel that we designed.
Like this is in vitro, and in vivo you have like different surface, right?
Yes.
So how do you account for that?
This is a physics model. It's less biology in this perspective. Yeah. So what we did, we don't take care of the different layers that we have, the surfactant or this.
We don't care about the behavior of this surface layer from an electric point of view, right?
Yeah, that you mean.
So how you mean the conductivity or what? Yeah. So we know approximately the conductivity of the tissue. And what I was really care about is the relaxation time, both of the aerosols in the air and also the relaxation time of the electrostatics effect. You mean the tau of how fast charge moving inside the tissue. And that you can calculate from two different properties of electrostatic, the dielectric and the conductivity. So if you're going to do this calculation, you're going to see that the time of electrostatic to react to a charged aerosol is so fast. It's a million times faster than the relaxation time. It's insane. So for that reason, you just need to have a conductive material beneath, and that's going to mimic the electrostatic properties, because this is going to happen faster anyhow. Okay?
With what people, did anyone try this with a real surface of a tissue, ex vivo model?
Yes. There are people. There's also the in vitro. In the in vitro, it's very common to use metals, aluminium and stuff like that as the conductive, or iron as the conductive layer. And in vivo studies, they just expose the particle and they see relation with the induced charge effect that I showed you before. So we can assume that the lung is a perfect conductor with infinite amount of charged particles, positive and negative. That's the way of thinking.
So someone did this ex vivo, kind of this work where you have charged different charge?
Yeah. I show you at the beginning. And also...
I mean ex vivo. Ex vivo with a real surface, not like a
They did in vivo. Like people inhaled charged particles and neutralized particles, and they saw the difference, and they compare and they saw that the proportionality of the deposition is dependent on the charge square.
I mean, it's okay, just asking that there is a gap here that in the field itself, like in vivo is a very tough scenario, and you get rough data,
Definitely.
Yeah. But ex vivo you can do more fundamental studies and control the flow, even image some of the things more. So there is still like a gap to show.
Yes, there's a big gap. This whole field of electrostatic is a very how you say it, not getting so much public relation. Like when I've been in a conference about the lungs, I'm the only one that's talking about electrostatics effect. It's a very narrow field, and the goal of this PhD is to expand it and to show how much it's relevance. That's what I try to do. But definitely, there's much studies that need to be done. And if Josué want to take it with more students, I would be happy to. Yeah. So this is the design of the microchannel, and
just
okay.
Scientific. Around me, everybody at this table knows, of course. He really said that maybe one next step is to cross a bridge between basically finding direct electrostatic attraction forces between particles and
living tissue.
Substrate that's tissue-like or ex vivo extracted, and do something crazy like an AFM experiment.
Yeah, conductive AFM. Yeah.
Because that's the kind of the next gap, which is there's no local data on measurements of conductivity of the tissue. It's kind of large scale, lung as a lung organ. So it's definitely a scale.
That's definitely going to be a very interesting paper, to take atomic force and see how much the spring extend because of the attraction to the tissue of some charge that are known. Yeah.
You saw it as like, I saw it as like, oh yeah, this is ISF stuff. Totally ISF stuff.
What about the temperature?
Wait. Yeah. So if you go in situ, at 37,
is there any effect on the
conductivity? Definitely depend on the temperature, but I don't think it would that matter, if to be honest, because the time scale of the electrostatics are so rapid compared to the relaxation time of an aerosol. So even if the tissue is a little bit warmer, let's say 16 degrees more, it would not change fundamentally the idea.
No, it may change the time scale a bit.
So it's going to be even faster. So it's already a million times faster. So
Yeah, just,
it doesn't.
just to understand what is going on and what is affecting.
Yeah, definitely.
And this is science.
Yeah, but if you think in an order of magnitude perspective, okay, so it's not going to change it dramatically.
Yeah, it depends on the temperature, of course, but it may change the conductivity.
Definitely.
And it may change the time of the position of the particle on the surface.
I think it's mainly would affect the diffusion. This is the most sensitive to the temperature. This is maybe a bigger gap that's going to play a significant role in the particle, much more than how much it changed the Coulomb force, from my perspective.
Yeah, but somewhere you take into account the Brownian motion.
Yeah.
In this scale, it may have an effect.
Yeah, definitely. That's true. I agree. So my models, all the experiments that I did were in the room temperature, but it's very fair and valid to say that everything should be a little bit more hotter. Yeah, I agree. Okay, so the idea of this microchannel is actually get rid of the high velocity and have a creeping flow, very slow velocity inside the acinar region as we have in the alveoli. So I'm going to show you this plane, the y=0 plane. So this is the diced glass, and we put on top a PDMS cover, and when using aerosol generator we produce air, and using the pipe we get rid of all the high velocity and sucked into the alveoli a very slow creeping velocity regime, a Reynolds of 0.4 in our case. And I wanted to show that as we discussed about the Reynolds, it's not the Reynolds of the particle, it's the Reynolds of the flow, but Reynolds is going down dramatically and reaching the creeping flow in the acinar region, and that's what we want to mimic in general. Inside the cavity, we have this shearing effect of the duct channel velocity, high velocity, which make a vortex inside our cavity, and that's exactly what we expect from previous studies in our lab and outside of our lab. So right now I want to focus on the exposure setup, how we produce the aerosol and how we examine them. So the size control is being done by choosing a polystyrene particle, which is known to gain a lot of electrostatic charge, and through two dryers also. And as a control group, we have the electrical neutralizer, which give us a Boltzmann distribution of charge, which is really low compared to the natural charging of the aerosol generator. And for the deposition, we use an inverted microscope to zoom into the region of interest, which is the cavities that we have. And here you can see a single alveolus. So this is a 3D image, and you can see that each sphere is a particle that we take a picture of a Z-stack. So we have the 3D image, and you see particle on the septa, inside the cavities, and here you can see the 6 alveoli, and you can see the size, the height of the particle with the color code. And I want you to already see that we have a lot of red, which means a lot of particle deposit on the septa. I'm gonna get into that later. So let's show you some typical result, and then we're gonna do some conclusion. So this is the naturalized case of 1.1 micron, which is known to be governed by gravity in this regime of the lungs. And if you look from the top, it looks like a raindrops. Particle falling everywhere, septa, alveoli. But if you're gonna flip the picture and look from the profile, we're gonna see homogeneous distribution approximately. And now the question is, okay, what would happen if the same aerosols were charged? So if I charge the aerosol, something very particular happen. Almost all the particle getting attracted into the septa, the spaces. So you see this feature. So electrostatic dramatically change the deposition pattern of this size of particle. And if I want to extend my result to get more close to reality, I need to face some of the design of my model. For example, my septa is 4 times larger than the real septa, which is approximately 10 microns. So in order to compensate for that, we calculate what is the concentration of particle that we have on the septa. We normalize by the area, and we can compare now the deposition fraction. And we did this experiment that I show you for 3 different particles, 0.2, 0.5, and 1.1. And we compare the ratio between how much particle we have on the septa versus how much enter into the cavity. So this one governed by gravity, this one governed by diffusion, and 0.5 is a convective particle. So we can see a dramatic change in the concentration of particle and the septa. From 10 we jump into 50. For half micron we double the amount of particle on the septa, and for diffusion particle we actually have the opposite effect. Now charged particle increasing the position inside the cavity, the random motion suddenly being guided into the cavity and not diffused outside. And something very interesting that I think should put much more attention, when I was in ISEM or in Ireland or all the other conferences, they always talk about the size of the particle. You want to get to the alveoli, you need this size. You want to, if there's no it's true. You see the light gray, it's changing. Okay, I agree, size is a very important feature. But I wanted to see what's happened when there's no regulation on the charge of the aerosol from the inhalers. All the results from all the size shrink to approximately 50. All the results. So we must have some regulation about the charge when design any inhalers. And another phenomena that happened, if we do a more resolution to... Okay.
This is in steady state, everything, right?
Yeah, everything is in steady state. Huh?
It's a good assumption?
Definitely. And you have the Wormsley number, and you can see that the time of inhalation, the period, is not that crucial, and so the flow would follow immediately, so it's going to be steady state.
No, but you don't have a pulse, right? You have
What?
In your model?
Yeah, it's a constant steady state, yeah, definitely.
So there is like a separatics kind of a flow is stable, so you, to go inside the cavity you need to...
That's a good point. So
prostate you're anyway inside, right? This is the...
Not exactly. Exactly, diffusion. And
anyway you cross it, electrostatic, diffusion, anything that is not driven by the flow, that makes the particle cross this stream, this specific stream.
Yes.
Would cause it to go inside, and then it's inside, it's trapped.
It's not trapped because diffusion can also take you outside. Yeah, and also think about that ideal cavity is that really flatter gravity. But in the real situation, the cavity can be upway, so gravity would actually resist from particle to go inside. So another idea that we had is to publish the same paper when it's anti-gravity. So yeah.
When these particles that are moving in single droplet streams, they're one after the other, right?
No, they're not one after the other. It's like, actually it's a really hard question to answer, but one can assume there's a normal distribution of particles that go inside the channel, and
they go as separated streams.
What do you mean separated streams?
They are arranged. First, you've shown us that it was like evenly distributed.
This is the deposition. I don't show airborne particle. Yeah.
The deposition goes like streams.
What do you mean streams?
Motion. Particles in motion. Go back.
Okay, yeah.
One more. Back. Back.
You want the CFD picture, right?
Yeah, here.
Here? Okay, this is the position. This is a particle that deposits.
What do you see on the right hand side?
Yeah. So what you see here, here I try to do like the cavities. So this high jumps is the septa. This particle deposit on the septa. They are not inside the cavity. And when they are charged, you see a lot of particle on the septa. So this is the next point that I want to talk about. So something about the electrostatic charge accumulate particle into the septa more often, but it's more related.
This is the view from above?
This is above, this is YX plane, and this is ZX plane. So this is from, where's the model? Here it is. So this is that, and here you have that. Here you see the cavities. From top, from profile.
The top one looks like strings.
Because it's just the bands of the hills and valleys.
Yeah.
I see what you're talking about.
Okay, but they fall. If you then look at this one, the one below, then indeed they go like lines which are settling down.
Yeah, settling down eventually.
Lines.
But the electrostatics confines them much more to the edges of the it's hard actually for them to go inside.
I'm going to show you. It's actually very related to your question. See, so this is the macro view, and this is the
Now you can see it in space.
Now you can see how much particle you have in the septa and how much you have in the cavity, and something very interesting happened against my intuition, that in this region I saw a depletion of particle. And when I look at what's happening in the septa, I saw that I have much more particles in the edges.
With your hands.
Yeah, so I also put a light here. So here we found most of the particles, and the reason we hypothesize it's happening is because the corner of the edge of the septa is very sharp. So more charges can accumulate on this tissue, and for that electrostatic love the rigs of the alveoli.
Nati, when I saw this, do you remember in the exam we were at in mechanical engineering? She does electrospraying, and they have a spinning disc where they sharpen the disc and it's rotating, and so the electrospray goes at the edge. It's this.
Yeah, so that was very interesting and surprising, but also makes much sense.
For the other, because I said before, you show percentage, but it depends also on the area, right?
Definitely.
So the area represents what is in physiology, or you should normalize the data by the area, right?
You saw the position fraction normalized by the area of my model, so it gives you a general sense. If you want,
there is a ratio between the area of the
alveoli versus the cavity.
Of the septa, right?
Yeah, definitely.
But in reality, the septa could be much larger than you draw it.
It's depending. The early generation, maybe in generation 15 or 16, yes, there's going to be a big gap between each alveoli, but it's very first become very dense, and the septa is 10 microns. Yeah. So we discussed that in the literature. We have a lot of discussion about the upper airway, and we discussed about the cavities, and the question remains is what's happened between. So I have two different projects that I want to show you regards that. So we're going to talk about the bronchioles. So we designed that model, which have generation 11, 12, and 13. And I'm going to show you this cross-section. We built it in a similar way to what we did before, a glass coated with ITO, PDMS on top. We control the velocity by a syringe pump, and this is the velocity profile. And something very important to consider, that our model has a square cross-section, and one can think that the lung is only perfect cylinders, but this is the Weibull model, and in reality, as deep as you go into the lung, the shape becomes arbitrary. So in this region of the lungs, it's a very good approximation also to go with the square, and the reason we did that is because it's easier to go inside a microscope and look what's happened on the glass itself. So also to produce it. So let's go back to the particle dynamic, and we managed to solve it numerically. So here you're going to see the particle trajectory, how particle y versus x, and as x I present the generation. So this is a nice demonstration, but this is the trajectory that the particle have when it's neutralized for a half of micron. You see that most of the particle escaping our model and would not like to deposit, but and of course they would have more deposition chances at the end of the model. They have more airborne time to deposit, but when we charge the simulation with the charge we expect to have in these aerosols, from the same height we saw something completely different. We saw that almost all the paths lead into the model. So the position, yeah.
Axisymmetric or
what do you mean axisymmetric?
I mean, you show us.
Okay. So if this is the channel, so I show you the mid plane. I didn't put here in the next slide I have. It's the mid plane of the channel. That's true. It's where is the parabola is at the maximum velocity. So the chances to deposit is even better when you get close to the edges of the wall, definitely, because it's slower. Yeah, so it's a representative, definitely. And I want you to see these sharp lines. You see them? So this is exactly the electrostatic force. In a short dt of time, suddenly you have a very big acceleration, and for that the particle deposit very fast. And so that's the Donald duck that I love, that show you exactly this pattern. Okay.
So this is like can you go the graph?
Yeah.
I want to see the length scale when this becomes dominant, right? It's like around
You mean this one?
30 microns, something like this, no?
Yeah, you see here, it's around the lower 5%. The lower 5% of the channel governed by electrostatic, approximately. Yeah, because you can think that this generation 11 is a little bit smaller than 1 millimeter. So that axis can be also as a percentage, you can think about it.
So you have it's super hot at 20 or so. Your cutoff is under 30 microns. And then if you think at your R squared, it means that you have a 1 over 20, 30 microns.
Yes, squared, exactly.
And that really blows up
everything, yeah.
It looks like just the percent, the trajectory depends when you reach this.
Exactly.
Yes, but something very important to notice is the flow is in the simulation. You see this dashed line? It's mean we're crossing generation. So the velocity here, the flow rate, because of mass conservation, is half what it was before. So if you would draw a line that show this capture zone, let's call it, so it's gonna be every time it's gonna jump a little bit higher. So that's the reason I hypothesize that electrostatic is dominant in the deep region, because this area it's very big compared to the diameter. That's the idea. It's the ratio start to begin to be similar.
Absolute value.
That's what's interesting is from an absolute value. He's right to say you still see more or less the same length scale.
Yes, yes. Yes, actually this is very...
It's not flow dependent or relative thickness dependent. It's not this annulus, it's not relative. It's an absolute number, which is somehow, it means there's a characteristic length scale of the electrostatic force.
Yes,
I think
so
that's a very good remark.
Yeah.
This goes to the fact that you're talking about the generation is just when this landscape becomes dominant. But
Exactly.
Around the,
I love this way of looking. Yeah, I love this way of looking. Yeah. It's a good way to observe it. Yeah. So not a way to the ink becomes significant, a way that the length scale of electrostatic similar to the diameter. It's a good point. I like it.
But the ink number has
a length scale
rewritten with that expression.
Yeah, definitely. Yeah. Actually, they do something similar when you define ink. So they put next to the R square, you need to normalize also R square. How you normalize it? So they put this similar idea, but I love your approach is more intuitive, I think. Yeah.
Only if the velocity goes down, like in every generation and so on, so other effects are becoming larger. Like
What effect?
other effects becoming more pronounced.
Definitely. So if you think about that, H, inverse Paclet, and charge, all of them depend on the inversity of proportionality of the velocity. All of them become stronger because all these non-dimensional forces are compared to the convective term, which is velocity in general.
And the Brownian motion becomes more prominent.
Yes, but something very interesting when you compare Paclet number and ink number of electrostatic is that Paclet also depend on the length scale, but the electrostatic depend on the length scale square. So the one that gain more from the shrinking of the sizes is electrostatic versus, so it's a battle between the diffusion constant, D, and between the charge multiplied by a Coulomb constant. This is like the fight that you really have in the properties, because the length scale is in the side of electrostatic. You see what I mean?
Yeah, but the diffusion becomes more significant.
Yeah, definitely. It starts giving a fight, definitely. Yeah, and something very important that me and Josue, it took us time to understand that. Like at the beginning, we thought about it's diffusion. No, it's electrostatic. No, it's gravity. It's actually electrostatics with the other mechanism. So that's what you actually see. Diffusion is always there, and gravity is always there.
Yeah,
And
but gravity will be less of an effect.
Size depends.
yeah, but the gravity give the particle the ability to be close to the tissue, and then they play together. Diffusion.
It's what Rami at the time when he was working on this, and he said, no matter what happens, you always you always obey the rule of streamline crossing. There's always one mechanism, either your self-diffusion, even if you have the weakest amount of diffusion or the weakest amount of gravity, in these length scales, you will always cross through, which was, it helped us understand that the concept of a reversibility for particle transport is so intrinsic to this motion that even when you do perfect matching of a perfect tracer in there, you are subject still to a little, just a bit of streamline crossing, and then it never brings you back to your starting point.
And it's hard to draw streamline in this.
And since it's a real particle, liquid or solid in air, there's always an element that will move you away from your original streamline, and you can't get away from that reality. And that helps understand macroscopically why there's so much heterogeneity. In and out will, just from that fact, never be the same.
Exactly.
This is why you have hotspots.
Absolutely. It all ties in, definitely.
Okay. So what we did next is we want to compare the result to the in vitro model that we show you. So we do see in the generalized case particles don't want to deposit. So we see particle deposit only in the end of the model. But when we have electrostatic, we see a completely different picture. We see homogeneously distribution across the model. So a lot of particles want to deposit. And that led me to, we wanted to go one step further with this model. And we designed a more sophisticated model than this. This is the one I showed you before, but this is the next generation of it. So this model is about taking care of also the bronchioles and also to compare electrostatic in the obstructive region of the lungs. So what do I mean by that? So when you have some constrictive disease in the lungs, so what usually happens is that the tissue becomes inflamed. If the tissue becomes inflamed, it's increasing size radially, but also minus radially. So the tissue is bigger, and also there's a lot of secretion of mucus inside the airway. So we end up with effective diameter of a disease situation, which is much, much smaller. How this affects the lungs, so we can think about the airway as a resistor under potential of difference. And this resistance of the airway is highly dependent on the diameter. So if the diameter decreases, the resistance is huge, and you don't have flow inside the sick places. So what usually happens is that COPD, chronic obstructive disease, asthma, is the third reason of death in the Western world, because when somebody inhales medicine, it doesn't go to the sick places. It goes to the small resistance airways. So, and I want to put that into a test because on the one perspective, when we think about the bronchioles, ink would be very strong. The velocity is small, the diameter is small, so ink would be dominant, especially in the case of constructive places. But don't forget that what's really governs the flux of the particle is actually the concentration of particle in the airflow. So this is highly dependent on the flow rate, and in these sick places you don't have flow rate. So it's two birds at one we try to understand. So just to give you a feeling, so we took the bronchiole that we had before and we constrict one of the sides. So we have normal versus ill, constricted. And just for a feeling, if you compare ink to H, the gravity versus charge, for different constriction, 10%, 20, 30, 40, 50, you can see immediately that the ink jumped dramatically. For example, for 30%, it's approximately 20 times stronger than gravity. But the price we pay is actually coming the flow rate. So you see for the different situation, the ratio is become very, very, very small. So you don't want to constrict the model too much. Otherwise, no mechanism will help you because there would be no concentration, no particle, no flow. So
this is measurements in your model, simulation?
Yeah, this was a measurement in my model that I compared different particles and always play with the constriction, did the theoretical of the resistance, and from that the flow.
Different models and different constrictions?
Exactly. Okay, so this is the design of the model. So we have the normal and the constricted. We decided to go with 30% constriction, not too much, so we're going to have flow. And Here you see a picture from the top of the model, and from a calculation of the flow, the nominal flow inside the model is 2.5 milliliter per minute. 80% gonna go to the normal based on resistance calculation, and only merely 20% to the constricted, from 30% constriction only. And what I want to show, and I want to show you like how the model, this is the experimental model, you show the here. So there's a reduction of the flow from the aerosol generator. We want to get to the laminar regime, and we control it with syringe pump, and we electrical grounded our model.
Can I ask you something about constriction? Because in blood it's very different.
Yeah.
Just to understand in the lab. So when you have a constriction, what you model in this model is this, like you have just the resistance of your system, but there is downstream resistance, right?
Definitely. Definitely.
So if the downstream resistance is much larger than the resistance where you are, so sometimes the opposite occurs in the blood system. You have the constrictions, but they almost don't affect the flow rate.
I agree, and I want to raise another thing in that approach. First of all, that's completely true. The resistance is actually what you carry is the total resistance. This this airway and also the next. It's important to take into account that the next generation connect in parallel. So that's for some degree reduce their effect. And again, this is just a lumped model. We show some constriction, some flow rate. It's true that we cannot mimic that.
It's kind of like saying, in a way, in our model, it's an excellent model.
Yeah.
The resistance after that, you have the resistance.
It's assuming that on the back end, each lobe is operating the same way in opening and closing, and it has one bottleneck here, and it has no bottleneck here. But the rest of the lobe is happy and doing great, and opening and closing regardless of inflammation. Upstream, or it depends how you look at it, because in the lungs, the proximal generations are basically upstream from where the flow is initiated. Whereas the heart, it's a downstream look, right? You pump from here and then you obey the resistance downstream.
Exactly.
And in the lungs is you suck naturally from the back, and so you're fighting for everything above you.
Definitely. I want to raise up something.
For the downstream in the heart, it's for sure, because if you have 20% stenosis, nothing will, like, this is why we're all good, right? We have some stuff. We're not losing 20% of the heart flow because of small stenosis. Only when it becomes.
You need to have a compounded effect, I would call it.
So when you do the calculations, you make iterations. Because like sometimes you have back pressure and you don't know it, you go from here to here.
Definitely.
So you look at the whole picture and converge. Right?
That's how it should be done. It should be done. In our perspective, and it's coming again to your question, is we want just to have some feeling. Okay, there's slower velocity in this side. There's some, the wall is closer to the particles right now because it's a constricted region. Let's compare healthy versus constricted and see what's happened to the particle. What you are both raising is the next step. I agree, definitely, you're right. You understand it right.
This is conceptually the P back, quote unquote, is maintained, right? Like the P on the back side, and then the delta P is the downstream, kind of the effect that happens after imposing the same P, driving P on the back side.
Yes, definitely. Don't forget also this is a steady state. So we simplify it by much. Okay, so
Would it be an effect if you have taken instead of channels, rectangular channels,
pipes?
Tubes.
How would it affect it? So the resistance would change immediately. Also, the velocity profile is different because at the corners you have a big region of almost zero velocity versus the cylinder, which is much more symmetric. But again, the lung is not either. It's not circular and it's not square. So
Not at those scales.
Yeah, not at those scale.
This is
Yeah.
another question. So
Yeah.
which one is more representative?
It's hard to tell.
Yeah.
We need to ask Weibel.
That's
Yeah, yeah.
I don't know. I think neither nor, kind of. Since there's so many hundred thousands of these guys,
Yeah.
they can be distributed across the circle to the square-ish.
I think one should do the average of.
Spheroids, I think.
Yeah.
I guess.
I think not the.
That's what he was showing from the histology cut. You kind of
Yeah.
see this kind of
Yeah, polygon shape. Yeah, yeah. It's hard to tell, but when I was a student a few days ago, you said to him something very right. So
study hard.
not you told them we don't want to do always experiment with the live thing because every time the geometry will be different. It's going to be hard for us to determine what key factor really change. So if we just have the same shape, it doesn't matter if it's square, if it's trapezium, if it's circle, it would stay the same, so we can investigate different mechanism and see when somebody play and overshadow the geometry and then change maybe the circular to square, but it must work in some geometry.
And you need some control system.
Yeah, exactly. Control system,
Especially
exactly.
since this is purely physics driven, let's be honest. You need it's essentially non-dimensional driven.
Yes.
So the minute we leave too much freedom, it's never going to
Yeah. So I won't come back to the simulation that I showed you before. And what I did now, I split the simulation. I release a particle at generation 12. This is the top view. And then I let the particle live in two olamot makbilim, parallel worlds. One that entered the constricted, one entered the normal. So you see that at the beginning they behave very similarly, but we start to see the diffusion play more strong effect on the particle in the constricted region because slow velocity and also the length scale. But suddenly in generation 14, what's noticed is there's some characteristic length that the particle being deposited around the 20 microns, okay? And the particle deposit, while the other particle in the normal area escaping the model and don't deposit. So just to have some feeling what we expect to have in the results. So maybe what's electrostatic do inside a constricted region. Of course, we don't know, and also concentration plays a significant role as well. If you have less particle, electrostatic is not there anymore because there's no particles. So what we actually got in the results, so this is a very diffusive particle, 0.2 micron, and this is the normal versus the constricted. So this is the deposition pattern that we have, and I think it's very interesting. In the normalized case, we see that approximately around 15% of the position fraction, and in the charge case, we see this drop, which means particle here screen to the particle here. And we can even see it better when we normalize by area. So when we normalize by area generation, we see here this downstream effect of concentration of particles because of diffusion mainly. And for electrostatic, this is very sharp. This is the superposition of electrostatic and diffusion.
So it's just, for me it was a very, very cool moment because we had a gut feeling that it would happen when we started the first paper with these alveoli.
Yeah.
But the thing is, we only had 6 alveoli, so we didn't have the long effect on length scale.
Actually, yeah.
But the point is that in physics, their screening, diffusional screening is an intrinsic problem where if you have a species that operates gradients through, you lose them early on, and then the downstream sees less because you've already hit the walls.
Definitely.
And in the lungs, when you breathe oxygen, you have that. On average, more oxygen molecules are basically a crossing or translocating into the entrance zones of the acinus, and the backside of the acinus that could get more, unless you suck in really more air, just is poorly utilized. This redundancy is to our advantage, of course, but the concept, and it comes from the diffusional screening phenomenon, which is
so it's not a particle base.
he has the
Yeah.
coupling, of course,
Yeah, yeah.
200 nanometer, so both exist, but you have this superposition effect of electrostatic screening.
And it's like, we're going to see it in a few seconds in the last project, but this start to open our eyes that the alveoli was not long enough, the bronchial was not long enough to understand and that's lead me to the last project. But last thing I want to show you here, that as you see the constricted region are not that affected by the electrostatic dramatically. This surprised me. So when we compare two different species that we did, 0.2 and 0.5, and we compare constricted versus total, of course in the constricted you have less particles, less flow, less concentration, less flux, but charge does not dramatically change the picture for that reason, okay? So yes, we answered the PhD question. Electrostatic plays a significant role in the deep region of the lungs, and we started to think bigger. We want to understand how electrostatic affect in a big scale all the lungs, because the airway don't forget each other. Like if there was electrostatic at the beginning, it's gonna affect the end, and there's a huge debate in the literature that one side of the researchers said electrostatic dominant in the small scales. That's me, I'm in that side. And a lot of people said, yeah, but electrostatic is the additive mechanism. So it's taking all your particle at the beginning, so nothing left for you to play with. So this is a big debate in the lung world, and we decided to come and solve it. So we tried to think bigger, and that's leading me to the last project, the one-path model. So how deep electrostatic particles can reach? And this is a very hard question to answer, because the geometry of the lungs is insanely complicated. And the best way to understand where particles are going to end in a real lung is to do gamma synchronotropy. You have a radio label aerosols, people, volunteers for money, inhale them, it's very pricey. And also when you compare where the particles are, it's not exactly tell you how much acinar, how much airway, it's perfect,
Just a short question. You take it as a one-way coupling, right?
What do you mean one-way coupling?
The particle is affected by the flow, and the flow is not affected by the particle.
It really depends, but yes, that's my assumption. Yeah, in my world, it's the assumption.
Some load particles, then there is an effect.
Definitely.
Adverse effect.
Also, drugs. Okay, what the classic relation to what you say. Okay.
I would say that this two-way coupling will affect the final destination of the particle. So was that taken into account? Because if you go to a very thin path, and even with load of particles, they will affect the flow, and then the flow will not carry it to the final destination that you think about. So did you take that into account?
I do not took that into account. You mean that the particle affect the flow pattern?
Yeah.
So no, usually in this world, in this field of the deep lungs, most of the people assume there's no effect of the aerosols on the vast air that we have, because the concentration of particle is very little compared. In the upper airways, in the mouth, probably this play a more significant role because the concentration of particle is huge. Also, in that world, it's very interesting also that the drag force is changing because one particle affected another. So it's what you say, it's very crucial in the upper airway for sure. In the deep airways, I think it's a very good approximation to regards it. Yeah.
I think it will have an effect even in the deep airways.
Because the ratio of scales?
Yeah, because if you have lots of particles and lots, even the low number of particles, still it's a high percentage of the cross-section that we capture.
Let's say a particle is 0.2 micron and it's entered the smallest region of the lungs. 600 times more bigger. So I agree. It's
you have 600 particles.
Huh? No, I don't think you have 600 particles. The concentration is reduced dramatically. It's every time all the concentration of particle, each division need to split, and smaller the group, you have 23 verification. It's exponentially decrease. It's in the smallest region, you also almost don't have group.
If you would take an oscillating flow,
Yes.
it surely will have an effect on the oscillations, on the local oscillations.
Yes, definitely.
But because you are taking a
Steady state.
maybe it's
Yeah,
it's okay.
agree. It's mostly because of the steady state. Yes,
And in the next stage, you need to take some
exactly. That's true.
oscillations.
There's a way to make the Aerosol generator work in a
No.
sinusal
No, but what you could do, you could think of a different system, which is
reservoir and breathe from the.
like his technique. So
Okay.
You would feed, and then we would oscillate from the reservoir.
Breathe from that
You could do it differently.
reservoir.
like that.
Okay, okay.
It's something
Then it's very
that
important.
you could do that. Voilà, c'est ça. Which is feeding off your aerosol source.
Okay, so since this is very expensive and not that humanitarian, you cannot do that on kids. Not going to work. So the most common solution is the cascading factor. You have a inhalation or from a inhaler with the FDA approval flow rate, and the cascading factor is a filter system based on the stock number. So the idea is you have a size distribution stage filters. So it's hard, based on the mechanical mobility of the particle, it's harder to go from one stage to the next. So they say that the first particle, which have a big diameter, would stuck here, gonna relate it to the position in the upper airway. In the middle, it's to the bronchioles, and the small particles that can reach the end of the model because they have such a small stock number are getting into the alveoli. And it's important to understand this is not anatomically driven. This is based on the mechanical property, which we say it's gonna affect their anatomical deposition. So it's not. But this is the most common method. Another approach is
Fancy, it's a, I don't even know if it's fancy. It's a particle sizer.
It's a particle sizer,
It's a
definitely.
particle sizer,
Yeah.
and then you
Interpolate the results. Yeah.
as if it were the places of the lungs.
Yeah.
It's about conventional. Like
So it came from a historical convention. Yeah. I don't know if you have similarities in the blood world, but for FDA approval, this is the gold standard.
Go to a regulation
Yeah.
for sizes from 2.5 PM 2.5.
But it's through factors, right?
Yeah.
It's historical.
I have an factor in my office.
A cascade like this guy? You have one.
Actually,
It's not like that exactly, but one after the other.
You have
the can. Yeah, it's a classic.
Yeah.
The classic one. Another approach to determine where particle going to go is using simulation. But it's important to remember that simulation is very limited because you give the simulation the equation. So you cannot get a new equation. So it's very good for validation, but it cannot work alone. And also it's very expensive in time and computer power. But something very interesting about simulation, that they found method to reduce the CPU power. One of the classic example is the trumpet model. The trumpet model based on the idea that instead of the complicated geometry of the lungs, we can take the bell of the trumpet and actually relate each region to the different region of the lungs. And in that case, what you actually do is taking into account the correct volume of the lungs and also the average velocity in each region is pretty much the same. So a simulation like that would start with the normal airways, and then only in the end of the model, when it's become very complex, you're gonna put this trumpet idea. And I very like this idea, and I never saw it in vitro design. So what I did, I decided that my asina region right now would look like this. I'm gonna use this trumpet idea, and so here you can see the ANSYS solution for the velocity flow, and here you can see it from the side. So that was the idea of how to build the asinar in my new next model that gonna present all the lungs. That's the motivation, that's the idea. And another approach that you see in simulation, it's the one-path model. The one-path model is genius. What the one-path model do is tricking the particle. The particle get into the junction and you see two options. Some airway model, and it doesn't know, but the other door is a bluff. There's nothing in the other side of the door, and the art is to design the door to be similar to what you have on the left. So what actually happened is that the particle enter, and it need always to take the right door. And if we go to the blue door, which means the exit, we're gonna count the particle, we're gonna understand what's the future of this particle because it's a mirror image. That's the idea. So what we did is we designed this model.
Because resolving all of it fully would be
Not
so costly and impossible.
Definitely. So that's a model, the model I designed. So you see you have generation 3, 4, 5, and in generation 5 you start to see these exits, which just get rid of the particle. They're not anatomically, only this path is the anatomically one, and it's ending up in generation 19 of the lungs, which means deep inside the acina where the position taking place, and it starts from generation 3. So basically I give up on the mouth and throat and have most of the lungs. The way I did it, you know, in the computer it's very easy because you just give the boundary condition, so it's be similar to here, but in reality you need to design the exits that's gonna give you the same flow. So this was the main challenge. So I use a matching resistance in parallel and series, and then I design it. But the biggest problem that I had is that the resistance was huge, and I could not change the diameter because then the particle would see huge door and a small door. Yeah. So it's not gonna be realistic, and I could not play with. I cannot increase L too much because it's become so long. So it's bigger than the microscope region that I have to play. So I came up with this idea that it's going to start the same, and only the end would change in diameter. So I did a trapezium exits, you see. So, and I come back with the theoretical value for the resistance for trapezium, and I did a normal resistance at the end, the curved one, to guide the flow. And we did some simulation to see that we have the real physiological flow in the lungs, and we did it. And we have a very laminar flow, fully developed in the deep generation of the lungs as we expected. And also I wanted to see that this is the velocity and the exit, 11, and this is the velocity profile in generation 11. It's hard to tell which is which. And that was the idea. And also when we compare this simulation to other simulation with the similar flow rate, we see that we actually have the same profile, the same order of magnitude. They use cylinder. It's important to say that they use cylinder and we use squares, but again, the lung is not either in this region. Yeah.
Is it likely that it's not just going down linearly, but maybe some constrictions? Some points you have like the diameter going down and up in some areas.
I think on average, no, but Josue maybe know better than me.
You mean even in the most healthy scenario?
Yeah, I think that maybe
it's hard to speculate. It could be
the tube is not just going one way, but maybe in some places like you have constrictions.
Yeah, that in other words, it just from its own loading or whatever, its compliance, because these are soft actually. So what's often forgotten is once you pass the main bronchi and so, actually all these airways are rather soft.
Yeah, they don't have the rings.
There's no ring, so there's a smooth muscle.
So the velocity can go up and down in some areas.
It could technically. I've never seen it really modeled. I've only seen when they look at instabilities of looking at basically collapsing airways on modeling these the flexibility.
Yeah, when you do suction.
Voila. That's one, exactly. But yeah, you make a point. This is extremely abstract.
This could affect the moving.
You could have in an ideal world, you could have the same model in a very flexible
wall
straight model.
Water envelope.
Right, and through your pumping, you witness localized events of either a kind of a folding.
And then we can have the hotspots suddenly.
Right.
Also, yeah.
Yeah, it's possible. Yeah? Absolutely.
Okay, so we made it. We have build the real model. I have it here if you want to see it. Here it is, start and then I give to Nati. I think Nati saw it already. So the idea is that we have actually two path models. It's symmetry. So we start generation 3, we have the outlet, and we end up in generation 19, and we know from the simulation what is the velocity profile. To validate the simulation, we also did a similarity experiment using water. So we expose the model into water with the particle, matching the Reynolds, and we follow, using the exposure time and the distance particle travel, we can calculate the flow rate in each part, in each generation, and also at the exit to see how it's distributed. And it's mainly distributed 50% as we expect in the deep region and not in the upper airway as expected. So in general, what we did is we stitch a lot of pictures. This is, so just to give you a sense, this is the 0.5 micron particles. So you can see it's square, and it's this square is become, I think you have here approximately 60 pictures, and for the 0.2, much more, like triple, something like that. So it's we don't have any space in the NetApp. I need to talk to you about it. So this is a very heavy, each experiment is very heavy. But in each experiment we see everywhere where are the particles. So this is a very cool transparent image. And for the neutralized case, you can see that we have that exposure, half of micron, and we see that the particle deposit a lot of here, and some of them reach to the acinar for half micron. And this is and you can also get into the acinar and see which generation got most of the particles. And something very cool that we can do. This is the real result. And want to show you next, it's some extrapolation of the data.
This is n equals 2.
This is n equals 2.
So now it's
Yeah.
just to give you a sense.
Yeah. Yes. So what I want you to see here that what?
It's in water?
No, this is aerosol in air. The similarity was just to validate the airflow. Just the airflow, yeah. So I need to change the color, not blue. Blue is kind of water. Yeah. So what I want you to see is, this is the real results, but we can extrapolate the result. Why? Because in a real case scenario, the one path model is not representative, because you have one trachea, two bronchus, and this become more and more and more as deep as you go. So the idea is to correct the result by area and also by generations. So if we do that, the results completely change. And we see nearly particle and some particle in the end of the model. You see it? And what I really want you to notice is we have here 82% within the model, and in the bronchial 18%. So now let's go back to the first graph that I showed you. So if we're going to take the deposition fraction that I showed you before, and we're going to zoom into the half of micron, so the ratio between each one of them is that the head gets 50%, 40, and 10. But we don't have the head in our model. So if we're going to subtract the head, we're going to get 80% alveoli, 20% terminal bronchioles. And that's a pretty good job right now. למה זה נחמד? טלוויזיה? בדיוק, in the moment of truth. Yeah.
The TV?
Yeah.
It's just because.
Yeah, I think it's become tired. Okay, so when we compare our result, we're very close to it. So we have in our model 80%, which is similar to 20, and 82 similar to 80. And now this is kind of a validation for us that we did a fair job. And right now the real question is, okay, Ron, bring on the electrostatic, let's see what's going on. So when we give the electrostatic, we see exactly what people said in the literature. So you're going to have a lot of deposition at the beginning, and maybe nothing going to left out to the acinar. But when you do the extrapolation, you suddenly see the charge reach to the deep region of the lungs and change completely the deposition pattern. We see that the acinar reduced by 50% approximately to 45, and we have some distribution along the model of charge. So we decided to go to 0.2 particles, and for the neutralized case, that's what we have. With the electrostatics, that's what we have, okay? And when we do the extrapolation, something very, very interesting happened. So you see that 90% should reach to the asinus, but when charged, only 55%. So where are all these particles? They accumulate in the bronchioles. The bronchioles, the terminal bronchioles, are the places where disease take place. And just for finish, I want to give you some food for thought. Let's say that in generation 3, okay, here in my lung, after my throat, 100,000 particles are there, okay? So if you're gonna go with neutralized case, 40% gonna reach to the terminal bronchioles, right? Which gonna leave us with 4,000 particles to treat this generation, COPD, asthma, any disease. And with the success rate I showed you before, we know the ratio, how much gonna get into the constricted region. And the result is that 1,700 would go there. Let's compare the charge case. If we charge the particle, 46,000 is gonna get there. And even though the ratio is smaller, it doesn't matter. We are order of magnitude succeeding to treat the disease place, which are unreachable with off-the-shelf neutralized inhalers. So the take-home message that I want to say and finish with that my PhD presentation is that the lungs is a very sophisticated device. From evolutionary perspective, from God perspective, each one what he believes, the lungs was designed to filter out intruders. And for that reason, it's very hard to treat the lungs with inhalers, the common inhalers. However, the body and the evolution never been exposed to electrostatics. Very artificial, strong electrostatic charge. And for that reason...
Is there any natural scenario where Homo sapiens...
Boltzmann distribution, mostly.
You don't have like a non-modern setting concept.
When you are in the desert,
so I'm asking, do you have like a natural exposure to it's charged air?
Yeah. Particles are charged when you have like a swivel.
How much?
You could just make a guesstimate?
Yeah, there was a research in Soroka that showed that in some days there were more miscarriages and stuff like that.
Seriously?
When there was a wind coming from the desert, and particles were not only charged, but they pushed forward a field with charge.
Wow.
I mean, the flow was charged.
Wow.
Not only the particles.
Ions.
Ions.
Yeah. Ionizer,
and then it affects your nerves. And at that time there was like a peak of things going on in the Aerosols.
It's crazy.
Yeah, it's interesting.
Very interesting.
Ionized air is different from. I don't understand some of these subtleties. The difference between, say, ionized air versus.
It's the oxygen. It's the nitrogen. It's not the aerosols. Yeah.
Also the aerosols.
The sense particles.
The sand particles are charged.
Yeah.
Yes.
And the gas particles, gas molecules are ionized?
Yes.
That's the language?
And usually the ionized gas is what charge the particle. So it's going both ways. Yeah.
You know, like in the movies when the dogs are saying, "Woo!"
Yeah. They feel the storm coming.
Okay, so I want to thank you for your time and also for the great team that I have in the lab. And that's it. That's what was my presentation about electrostatic effect in the deep region of the lungs. And if you have more questions.
Questions to the examiner?
By the way, in COPD and bronchiolitis and
Yeah.
CF and all these kind of illness, you have blockage of the airways.
Right.
You have mucus, so the particles cannot reach the deep enough.
It depends how much. Usually it's a layer that it's not always 100% blockage, but it's a gradual. If you don't treat it, yeah, it's going to get to 100% blockage, yeah. And then they lose parts of the lungs. They have smaller lungs. And
So this is a problem what you're saying, because charged particles would be cleared in the mucus, right? Where you have this mucus.
Yeah, will be captured by the mucus.
Yes, captured
And only if you manage to take out the mucus by physiotherapy or some mechanism. Because in the intensive care unit, the pediatric intensive care unit in Soroka, they have lots of kids coming with CF or bronchiolitis, where we have an increased amount of mucus.
Absolutely.
And we actually treat it in my lab. We have a device developed with oscillating flow and acoustics together. So
wow, this is very cool.
It is.
So after we clean the lungs, you can use your
Definitely. Let's work out together. Let's make it. Yeah, definitely.
do a single device. First cleanup, then drug delivery.
Very cool.
Yeah.
Nancy, you want anything? All good?
No, it's good.
All right, so maybe step out for a second?
definitely. נסגור את ההקלטה גם.
בבקשה.